Thanks a lot for the introduction and the opportunity to tell you about our work on the fundamental limits on general quantum resource purification tasks and their applications. So this is going to be a unified talk introducing the list of 3 papers where paper 1 was from 2019 and already published, which first for the theory of general no purification bounds. And paper 2 and 3 are more recent extensions to channels with new methods. Paper 1 and 2 are joint work with Fang from Baidu Research, and number 3 is by Bartosz Regula, who will be giving part 2 of this talk, and Ryuji Takagi. So here's an outline of the content. Our general results are bounds on the accuracy as well as the efficiency of very general resource purification tasks in both state and channel setting. And we will introduce 2 approaches to deriving these bounds. In part 1, I'll introduce what we did chronologically and focus more on intuitions. And in part 2, we will hear more about specific results from Bartosz. We will also discuss the implications to a series of practical problems, including magic state distillation, quantum error correction, and quantum communication. So to begin with, the key problem we would like to address here is noise, which is a notorious obstacle that prevents us from already having large-scale quantum computing and other technologies. This is because quantum systems and quantum information is intrinsically very susceptible to all kinds of noise effects. Mathematically, the noise generically makes the ideally pure systems mix so that the system become unreliable or lose power. The community has been developing and improving many important methods such as quantum error correction, error mitigation, and distillation in order to battle with noise. But so far, there's not much systematic understanding about their ultimate performance in practical scenarios. And this is what we hope to address in this talk. The next thing we need to introduce is the notion of quantum resources. We learned from economics that things acquire values as resources when they're useful but hard to get due to certain constraints. So here in our physical context, the practical setups will place constraints on what you can easily do to quantum systems, and these constraints will induce certain resource features. Prototypical examples in quantum information include entanglement and magic states, but there's actually a wide variety of different forms of quantum resources that could emerge in different contexts. The manipulation of these quantum resources underlies all kinds of quantum information processing tasks because they often serve as the origin of the quantum advantages that we want. The so-called quantum resource theory provides general language to characterize and study the manipulation of quantum resources. A resource theory is defined by free states and free operations, but here we only care about one minimal golden rule, which is that a free operation must map free states to free states. In principle, the set of free operations can be defined quite flexibly, but the point is that any non-trivial one should be contained in this largest non-generating set. And so what cannot be done under this condition is considered impossible in any non-trivial resource theory. So the general task we're going to consider now is to transform a noisy mixed state to some target pure resource state by free operation, maybe probabilistically, and some error could be allowed. As we will further see, many important tasks in practical quantum information processing may take such form. And what we are going to show is that there are universal no-go theorems, or namely lower bounds on the error on such kind of tasks that apply to any well-defined resource theory for any pure resource target state and under any free operation. As a quick summary of the intro, the talk concerns altogether the practical problems of noise and restrictions in practical scenarios and finite resources, or namely we're considering this one-shot setting in contrast to the asymptotic setting. Now let's see the first proof, which can be explained by resource measures. For meaningful resource measures, the most basic property is this monotonicity property that they should not increase under free operations. That is, a state with a smaller value can never be transformed to a state with a larger value under free operations. So here, our idea is to consider a very special monotone induced by the so-called quantum hypothesis testing relative entropy defined like this, which is a suitably smooth version of the so-called mean relative entropy. The resource measure is given by minimizing over the free states sigma. And due to the data processing inequality of this divergence, we indeed have a monotone. So to get intuition about why this monotone is particularly useful, let's set epsilon to 0. And then this operator P becomes a projector onto the supportive row. And then we can easily see that the monotone will become 0 for noisy states, but it is positive for pure resource state. And note that the smooth version has good continuity properties. So for small error, this order is roughly preserved. And then we can derive lower bounds on the error by analyzing their detailed behaviors. With a little tweak of the analysis, we can also deal with the probabilistic case. And the overall result is this forbidden regime of the achievable accuracy and success probability, which depends on the properties of the noisy input state and target state like this. Such error bound can actually be applied to this more widely studied distillation setting, where one roughly intends to extract high quality target resource state from a large number of noisy initial states. Now we are interested in the number of copies n needed to achieve some desired accuracy, which basically characterizes the cost of the protocol. The error bounds can be translated to bounds on n, and in particular in the small error limit, we get that n and we'll discuss magic state distillation more specifically later. So before introducing the second approach, let's define a very useful extension of the resource theory framework, where the resource objects are now quantum channels, and the manipulation are described by channel-to-channel maps, or the so-called supermaps. This generalized framework is necessary to discuss, for example, Shannon theory and circuit synthesis problem, and it is in recent years. So here in particular, the counterpart of the purification task is to simulate a unitary channel by noisy channels. A key subtlety of the channel theory compared to state theory is that multiple inputs can be composed in presumably inequivalent ways, such as in parallel or sequentially, or even in more complicated ways. So the generalized purification task for channels here is to transform multiple copies of channels, which can be used in different ways, to some unitary target resource channel. So the second method is based on an even simpler idea. The idea is to decompose the noisy state into a probabilistic mixture of a free state and something else. Simply speaking, by the golden rule, the free component in the initial state will remain to be a free component in the output state. So we can see that the output cannot be exactly the target pure resource state. Then by quantitatively tracking this process, we can obtain new error bounds, which mainly depend on the size of the free component. And this idea can be easily adapted to channel theory with multiple inputs, and we can obtain very powerful bounds. Here I was very brief about this method, but in part 2 by Bartosz Regula, there will be more detailed discussions about it. Now let's see some application of the above general theory. I'll first discuss the magic state distillation problem, which is an important approach for fault-tolerant quantum computing. So the idea is to produce high quality T states offline and then use them to emulate T gates in the circuit, which are hard to protect, but necessary for achieving universal quantum computation. A common formulation of the magic state distillation task is as follows. So the input is n copies of noisy states rho, and the goal is to output with some probability a state whose each of the n marginals are epsilon close to the T state. And the question is how large the total overhead n has to be. And by refining the general methods, here are the explicit bounds on n that we can obtain. So as you can see, n indeed scales at least logarithmically in 1 over epsilon, and the quality of the initial noisy states is encoded in the base of the log. Now let's make some direct comparison to the efficiency of magic state distillation protocols on the market. So the most studied kind of protocols are based on using stabilizer codes and then reiterating the quantum error correction procedure until you reach some target error. And the key parameter characterizing the efficiency is the exponent of in the average overhead n over m. Then in this language, the key implications are twofold. So the first one is that any sub-logarithmic protocol, such as the recent breakthrough one by Hastings and Ha, must have a diverging size output so that the overall cost could be pretty bad. And the second one is that for a large class of codes, such as k=1 codes, indeed the average overhead will have the exponent is indeed provably lower bounded by 1. And the next application is about quantum error correction, where the encoder and decoder are subject to certain constraints. Here, the key observation is that such error correction tasks can be formulated as purification in both state and channel setting, because the goal is to recover the pure logical state or to simulate the identity channel. So here, let's focus on the case of covariant quantum error correction, where the codes are subject to symmetry constraints. There are many good motivations to consider covariant codes. For example, it is closely related to the Easton-Knell theorem, and it is of a great interest in a wide range of physical contexts because quantum error correction and symmetries often arise. So then by the insight of treating covariant quantum error correction as a purification problem, we can derive theoretical limits on the accuracy using the resource theory methods. And I notice that here we are considering continuous symmetries. Relevant discussions can be found in our paper 2, as well as this other paper joined with Zi-Wen and Jiang. In particular, in that paper, we analyzed another monotone based on the RLD quantum fission information that works pretty well for this problem. And we also use quantum metrology to derive a bunch of bounds. So if you're interested in these techniques or this topic, please also check this paper out. So in the paper, we also studied implications to quantum Shannon theory and the noisy circuit synthesis problem, but due to time constraint, I will not go into any detail now. So please refer to the paper for details. And in part 2, Bartosz Regula will give a more comprehensive discussion on quantum communication. So thanks for the attention, and I will now hand the mic to Bartosz.
Thank you, Zi-Wen. So let me introduce now the speaker for the second part of the talk, Bartosz Regula. Please, Bartosz, take it away. You can share your screen.
Okay, do you see the screen?
Yes, please, go ahead.
Thank you. And yeah, let me begin by thanking the organizers quickly for this opportunity. The results I'll be presenting are from a joint work with Ryuji Takagi, who's at NTU in Singapore now. And they overlap a bit with what Zi-Wen was talking about just now. So I'll try to focus less on the overlapping parts and more on the extensions that we do. So the overall setup is very similar. So we have a quantum channel, a noisy channel that we want to transform into some target channel. The target being some pure, so either a unitary channel or a replacement channel with a pure output here. The crucial idea here is that this is a free transformation. So the supermap is a free operation in some resource theory defined by this set of free channels F. The error here will be measured by the so-called worst case fidelity, which is a bit different from the metric that Zi-Wen employed in his part of the talk. And this quantity is related to the diamond norm distance. So if you prefer, you can think of the bound in terms of the diamond norm as well. Now, to bound this error, we will employ two different resource measures. One is the resource weight, which you've already seen in Zi-Wen's talk as the free component. And this can be understood as the kind of optimization and inequality at the level of positive semi-definite matrices. And if we just flip this inequality, what we get is a different measure called the robustness. And this robustness can also be understood as kind of convex optimization, convex mixtures of this channel with some noisy channel N. And the crucial idea here is that if F is a convex enclosed set, as it usually is in most kind of settings of interest, then these two are convex optimization problems, and they become easy to characterize and even computable in many cases. So this was our assumption here, that F is a convex enclosed set. Our first result then is that for any distillation protocol, we establish two universal lower bounds on the error of distillation. So again, any transformation that performs, any free transformation that performs the distillation up to error epsilon can, or the purification protocol that up to error epsilon, is lower bounded by two bounds. One depends on the weight measure, one depends on the robustness measure, and this F of T is a fidelity parameter, like it measures the overlap of the target channel with the free channels. Now, these two bounds might look similar, but they are very different from both a quantitative and qualitative perspective. And as we've already heard from Zi-Wen, when, for example, when this weight is non-zero, then we see that zero error distillation becomes impossible because this bound prevents epsilon from being zero. On the other hand, the robustness can apply in other settings. For example, when when the input channel is unitary, the weight becomes zero, and this bound is useless. However, the robustness bound can still provide useful information, even, for example, for pure channels or for pure states as input. Now, these two are generally applicable universal bounds, but the kind of a major strength of these two bounds will actually be in the multi-copy manipulation. So we've already seen that channels can be manipulated in many different ways, and indeed there are even more general quantum processes that don't impose a fixed causal order between different channel uses. And so our next result is to show that for any such multi-copy distillation protocol, it can be parallel, sequential, adaptive, or it can have indefinite causal order. Any such protocol which takes any uses of a channel and outputs a channel which is epsilon close to the target, the required number of uses is lower bounded by these two universal bounds. One depends on the weight measure, one depends on the robustness. And again, these two measures will be very different. So here, this is the scaling that Zi-Wen already talked about, that when we take epsilon over to zero, we see that the n, the required number of uses, has to scale as log 1 over epsilon. The robustness bound, on the other hand, it will come into play in a different asymptotic setting. So it will be useful when n goes to infinity. And here we understand asymptotic distillation rates. So what I mean by a rate is when we transform, I have a protocol which takes any uses of a channel and outputs some number of copies of the target. Here we impose that the error goes to zero as n goes to infinity. We can then define two different types of rates. One being the adaptive rate, so the largest achievable rate under all possible general adaptive protocols, and one being the parallel rate, which uses only these parallel manipulation schemes. A very related concept is the strong converse rate. So a strong converse rate imposes not that the error goes to zero, but that the error goes to anything that's less than 1. So the main idea here is that the strong converse rate establishes like a fundamental threshold on achievable rates, because any rate which is larger than the strong converse rate will have the error going to 1 necessarily, so it becomes useless. Now our next result is to show that the strong converse rate of any distillation protocol will be upper bounded by the log of the robustness measure. Here we make an assumption about the structure of the target channel, but this will be satisfied in all of the cases of interest, so it's more of a technical assumption for these cases. And for parallel manipulation schemes, we can actually get a tighter bound by using so-called regularized robustness measure, which essentially tries to understand the behavior of the robustness in the asymptotic limit. So this might look a bit scary, but it actually is computable in several different cases, and we can use that to establish tighter bounds in several contexts. So now I've shown 3 different ways to establish general limitations on distillation. Now let me quickly talk about applications in some practical settings. Quantum communication is one such major application. This set can be understood as Alice and Bob trying to distill a noiseless communication channel. So that's why this distillation framework or purification framework, it can be applied in the communication setting. Now the question becomes, what are the 3 operations here, the 3 transformations? There are 2 different approaches. One is to allow Alice and Bob to perform classical communication, to assist quantum communication, in which case the 3 operations are the LOCC, or local operations and classical communication. Another approach is to allow shared correlations, such as entanglement. The issue with these sets is that they are actually very difficult to characterize. So what we can do is approximate them with commonly used approximations and to get useful upper bounds. We will use separable operations and PPT, or positive partial transpose operations, to approximate LOCC, and no signaling communication to approximate entanglement assisted. And here already at the one-shot level, we can compare our bounds with the achievable no signaling rates because they are computable by SDP. So we see, I don't have much time to discuss this, but we see that the rates become, in some cases, they become tight. In some cases, in all cases, they provide useful kind of approximations of the achievable error. But for communication, the interesting kind of aspect is the asymptotic rate, or the quantum capacity. So for this case, for no signaling as the upper bound on quantum capacity with no signaling assistance, we get this regularized robustness measure. And again, this looked a bit scary from the definition, but in this case, actually, it is computable, as it has been shown recently. It reduces to the mutual information of the channel, which allows us to recover the result that this is a strong converse rate of no signaling communication. For separable and PPT assistance, we get that the quantum capacity, or strong converse capacity, is upper bounded by the log of the robustness. And this quantity actually already appeared as the max relative entropy of entanglement in a different work. In a very similar way, we showed that the PPT capacity is upper bounded by the log of the robustness, which is very closely related to a different measure that was employed recently. So the point here is that we recover all these different results from different works in a kind of a single unified formalism. And this simplifies the proofs in many of these approaches and shows them all to be part of like this broader resource theoretic framework. For magic state distillation and gate synthesis, we can also apply this straightforwardly. We can apply this either at the level of gates, so the channels or unitaries themselves, or at the level of state manipulation in the form of magic state distillation. And here we, for example, we see that the robustness bound can reveal errors when the weight bound fails. So for instance, here in the noiseless case or low noise case setting, the robustness tells us that, for example, a T gate cannot be converted to a CCZ gate efficiently, which is expected. Here we see, even in the, when we consider more copies, we reveal errors here, and the bounds perform significantly better than the previously best bound, which was the eigenvalue or hypothesis testing based bound that Zi-Wen talked about in the first part of his talk. Now, the strength of the weight bound will be obvious when we consider distillation overhead. So here we see, for instance, that the weight bound performs significantly better than previous bounds, the other known bounds, and to our knowledge, it is the best available bound for a general bound on magic state, lower bound on the magic state overhead. Now, as a final remark, these bounds can be extended to a setting where the protocols can fail with some probability, so they can only be realized probabilistically. And we get useful one-shot bounds in such settings, but this becomes more tricky to investigate, for example, asymptotically, because there's trade-offs now between the error, the resources, and the probability, and the bounds become much more difficult to understand, but nevertheless, we get useful expressions for such bounds. Now, to conclude both parts of this talk, we established a general approach to universal practical limitations, in particular of tasks involving purification of noisy resources on quantum channels or quantum states. We gave computable bounds, quantitative bounds on the error and the rates of distillation. These bounds established powerful no-go theorems and fundamental thresholds on achievable performance. and they can be applied in a broad variety of physical settings and different applications. And one thing I want to stress with these points is that we really make very few assumptions about, we allow general protocols and general resources, and these results hold in very, very general settings. And as such, they can be understood as a fundamental principle of quantum mechanics, because we really don't assume much in addition to the basic structure of quantum mechanics. Open questions are about achievability. So to what extent we can achieve these bounds? For example, they can most likely be achieved in general asymptotically to some extent, but we don't know to what extent they can be achieved in practice. But the main open question here now is just for you to apply this to your favorite setting of choice, because these bounds really do apply everywhere. So I hope that you can find interesting applications of them. Thank you very much.
Thanks a lot. Thank you both for your very nice presentations. So let me relay a question from Slack. So the question is for Zi-Wen, so corresponding to the first part of the talk, and the question comes from Isaac Kim. So you say that in your paper you have the bound on magic state distillation is applicable also to code-based approaches. And the question is, if you can clarify a little bit what you mean about these code-based approaches. And for instance, you mentioned that the Meyer-Easton-Kneel approach is a code-based approach. And if you could add some details on this, Zi-Wen, please.
Yeah, sure. Can you hear me? Sorry.
Yes.
Okay. Yeah. So what I mean is that in the code-based approach, there is an implicit assumption that the transformation still needs to be a stabilizer operation. So that's why we're talking about stabilizer codes. Then it just satisfies all these assumptions we had, like the operation must be free, and we are transforming a resource state to some other resource state, and that's why the bound applies. Does that answer your confusion?
I hope so. Thanks a lot. There is another question, I think, now for Bartosz. And the question is about the difference between these adaptive and parallel schemes. So the question is, in which problems does the adaptive setting, the adaptive scheme, outperform the parallel ones?
Right. So well, the answer is no, because we cannot reveal anything about them, because the idea of the bounds is for them to apply in all settings. So they have to apply to both adaptive and parallel schemes. There are tighter bounds, but they will generally be incomparable. So it is an open question, essentially, to understand, or for example, to establish tighter bounds under some more assumptions on the protocols. This is an open question. Our idea was to have bounds that apply essentially in all possible cases.
Great. Thanks a lot. Thanks to the both of you, and thanks for all the speakers in this morning session for the very nice talks. Before I log out, let me remind you two things. There are roundtables associated to each talk, and they will start at 10:30, I think. And also, second thing that I want to remind is that at 10:45 there is an opportunity to be part of the group picture of QIP, which will be done via Zoom. So information on how to do this, how to be part of this, will be on Slack in the meet and greet channel. So people who haven't done this yet, please go ahead and take part of this group picture. Thanks a lot.